Okay, so this is the first problem from the second problem set from David Tong's lecture notes. So it's just working with the Hamiltonian for the string problem that we did in the first problem set. And basically he just says, given these commutation relations for our generalized coordinates and momenta, and given these definitions for our raising and lowering operators, show that these operators obey the usual or some specific kinds of commutation relations. So, for example, if we compute the commutator of an with am, using these definitions, you'll just get these four kinds of terms. And then using our commutation relations for the coordinates and momenta, so this term will be 0, this term will be 0, and then this term will be minus this term. And so you'll get 0, which is what you would expect. And then similarly, for the raising operators, it'll work out kind of the same way. And then for the commutation relation of a lowering operator with a raising operator, it's written out like this, and then again this term is 0, this term is 0, and this time these two terms will add, and then using this relation you just get this. So that's fine. And then it says, what is the next thing it says, okay, show that you can write the Hamiltonian as this thing. So to do that, all you have to do is invert these relations between the coordinates and momenta and raising and lowering operators. So you can write the coordinates and momenta in terms of those like this. And then it's just a matter of computing these Hamiltonian terms. So I do that here. And then you just plug those into the Hamiltonian, and you'll just immediately get this kind of expression. And then it says, okay, so show that you can write the Hamiltonian after subtracting the vacuum energy as just this thing. And to do that, you just, so if you calculate the expectation, or the energy of the vacuum state, so if you just act H on the ground state, then, okay, this term has a lowering operator, so that'll annihilate the state, so that goes away. So we'll just be left with this term. And then I can use my commutation relation between an and an dagger and get this. And then again, this term will go away because the annihilation operator annihilates the state. So I'm just left with this. So this tells me that the energy of my ground state is this infinite sum of 1/2 omega n. And just like in the field theory, what we did is we just subtracted away this infinite ground state energy. So we kind of redefine the energy of the ground state to be 0. So if I take my Hamiltonian and I just define it to be, what we had before, only minus this 1/2 sum over omega n, then I can write it like this. And then I can use, so again, our commutation relation, an dagger minus 1 is equal to an dagger an. And so I end up with just another factor of an dagger an, and that will cancel this 1/2. And so I get this expression. And so it's kind of like, the normal ordered version, Hamiltonian, of the Hamiltonian. And then finally, we want to compute this commutation relation between the Hamiltonian and the raising operator. So if you do that, you have this, triple commutator, and you can use one of the identities for 3 operators to split this into the sum of 2 kinds of commutators. And obviously this one will disappear because it's 2A daggers. This one sticks around. You can use the commutation relation, so you just get that this commutator is proportional to the raising operator. And using that, you can calculate the energy of your excited states. So the energy of a state with, excited in the mth mode, you just use the commutation relation that we just found here to get this. And that just tells you, so this term will go away because the Hamiltonian, we've redefined the Hamiltonian to give 0 when acting on the ground state. And so this tells us that the energy of the state is just omega n. And similarly, you can do that with not 2 particle in this case, but 2, excited modes. Again, just use the commutation relations, and this time you get omega m plus omega b for the energy of that state, and then you can generalize that to this kind of arbitrarily excited state with L1, A1 excitations, L2, A2 excitations, all the way up to Ln, An excitations. And this will just be, L1 times omega 1 plus L2 times omega 2, and so on. Or written more compactly like this. So I've gone through this kind of quickly because I don't think it's, there's nothing too challenging about all of this. But for the sake of completeness, I felt I should go through it. So, yeah, there you go.